Hello, everyone. This is Omar Silverman. And on behalf of the co-organizers of the GDJC sessions, I am happy to welcome everyone and introduce Lauren Wedekind, who is a co-organizer, and she will be presenting on this topic on investigating the relationship between birth weight and type 2 diabetes. And one thing that you should know is that tomorrow she's defending her dissertation. And this was just one component of the full story of her dissertation. So welcome everyone, and thanks, Lauren. It's over to you now.
All right, thank you, Omar, and great to see everybody here. Really looking forward to talking kind of high level for a general audience about my research. And because this is being recorded, just if you have any questions, if you could just hold them to the end. We normally have 15 to 20 minutes worth of question time, and I'm really happy to hear any questions. So the reason why I wanted to offer this session to the public and invite friends, family, colleagues in diabetes epidemiology is because in going through my thesis writing process and getting ready to defend over the past year, I just thought I was reflecting a lot about how kind of opaque the process can be. It can be quite intimidating. It can be very difficult to envision how you can put together a PhD project over time and then eventually see maybe sharing to the public in a dissertation form, in a lecture form when you're actually defending your dissertation thesis, and also in publication. So hopefully this gives you a bit of an idea of how I've gotten to write and now getting prepped to defend my thesis tomorrow on this relationship between birth weight and diabetes that I've been investigating. And if you have any questions about this process, feel free to bring them up here or online later. I'm really happy to be open about the process. All right. So this thesis dissertation review basically is kind of centered on a theme of investigating the relationship between birth weight as a marker of early growth and later on type 2 diabetes risk. And a lot of people, when I first bring up that I investigate this relationship, are kind of confused, like how can something that is evident so early on relate to a subsequent risk of something years and years down the road, sometimes decades, in terms of type 2 diabetes. So I'll try to go into that and then kind of situate my different projects within this larger landscape of really exciting epidemiology research, and hopefully get some of you excited about different things in diabetes and life course and genetic epidemiology, because it's kind of at that intersection. So for a summary, there's a lot of different types of diabetes beyond just type 1 and type 2. So as you can see on the left-hand side, there's type 1 diabetes, or T1D on the bottom left-hand corner. T2D, or type 2 diabetes, is something that maybe many of our friends, family members might be at risk for, have prediabetes, or they might have. And there's a pretty heterogeneous collection of different kind of manifestations that type 2 diabetes can have. So as you can see above, some people tend to have insulin deficiency. So that's a hormone that helps regulate blood sugar in the body, along with glucagon. And then there's also people who have type 2 diabetes, but they have kind of defective secretion of insulin in their bodies with defective insulin, basically insulin resistance. So their tissues in their body resist the effects of insulin for whatever reason. I won't go too much into that because that's kind of beyond the scope of this presentation, but just know that type 2 diabetes, or T2D, is quite heterogeneous. And that's going to be a really big focus of the research that I try and highlight later on. There's also other diabetes types, and a lot of people aren't aware of this. So diabetes can be secondary to some diseases of the exocrine, basically like the pancreas functioning as a gland. Also monogenic onset diabetes of the young, or MODY, which I'll touch on really briefly later. And then other different types of diabetes that are rarer. But this is something, this schematic, I wouldn't have understood before I began my PhD, really. All right, and then I'm going to be focusing on type 2 diabetes. So going into kind of life course epidemiology, this is something that I got really interested in as an undergraduate when I was kind of looking at the early life influences on later risk of disease in our biology classes. So first, there's something called the Barker hypothesis. Maybe you've heard of it, or maybe you've heard of this concept of developmental origins of health and disease. This is this concept that came about like a few decades ago, and it tries to relate nutrition, so basically in utero nutrition, mostly maternal nutrition, with early growth. So if a fetus is exposed to a normal intrauterine environment where they're getting basically exposed to the parent's nutrition at a normal amount, then they're likely going to have normal birth weight. Pretty standard. And then that offspring will have more than likely normal energy intake later, and then less risk of metabolic syndrome. That's what the hypothesis said. And then on the flip side, you see on the left-hand panel, this image is where there's malnutrition in the in utero environment, basically in the uterus. And that leads to basically the fetus getting less nutrition, having lower birth weight, and later on actually having a higher risk of developing metabolic syndrome because there's kind of adaptive mechanisms that cause a higher energy intake. So this is all a hypothesis that came about some decades ago and gave rise to tons and tons of research looking at the relationship between birth weight as a marker of that early growth, that early nutrition, and exposures in utero to later risk of type 2 diabetes and other cardiometabolic diseases. So like heart disease later on, other metabolic syndromes that they just summarized using that term. All right, for more background, so why investigate birth weight and type 2 diabetes? So some studies, so epidemiologic studies looking at kind of risk of disease and development of disease in multiple populations have actually shown that birth weight is associated with type 2 diabetes in adulthood and quantified that. So I'm just bringing up some figures from a pretty big meta-analysis in different study populations that was done before my research. So in the Canadian general population, there's this relationship where you can see birth weight on that horizontal axis is positively correlated with risk of diabetes. And then in certain other populations, you can see more of a U-shaped curve, or kind of like these bars that show the confidence of where birth weight actually falls with respect to diabetes prevalence, kind of shifts a bit. So yeah, you can see overall, there's kind of a positive correlation, as in like a sloping up towards the right, but some can look more U-shaped, and I'll go into that in a second. So why would a relationship between birth weight, meaning low birth weight on the left-hand side of this graph, and high birth weight on the right-hand side of this graph be interesting to investigate? Well, on the left-hand side, one thing that we talked about was with the Barker hypothesis, or the developmental origins of health and disease, was talking about malnutrition exposure in utero associated with low birth weight and higher risk of diabetes later on, this left panel. So there's non-genetic things that can influence that. We talked about the poor in utero nutrition reducing birth weight. But also genetic factors can also associate with low birth weight. And I'll talk about that a bit later. Also on the right-hand side, type 2 diabetes can also be associated with higher birth weight. So non-genetic factors can influence this as well. So the offspring of parents with type 2 diabetes can have higher birth weight because they're exposed to in utero environments with greater amounts of blood sugar. And also there's genetic things that can influence that as well. So certain variants within the genome, DNA, can associate with higher or lower birth weight on this genetic side below. All right, so also work from my research group that's based in Phoenix has been really brilliantly done, looking at diabetes in parents versus birth weight. So if you look on the x-axis, the horizontal axis, there's these different categories. So if neither parent had diabetes, birth weight was relatively, well, let's just say that that's the reference category. Whereas if both parents had diabetes, then birth weight was kind of relatively in the middle, like around 3,600 grams or 3.6 kilograms. If the mother had diabetes, then birth weight was relatively high, and this difference was significant, as you can see from the bars. And then if the father only had diabetes, and the birth weight was relatively low. So kind of looking at these different, like the fact that the parent of origin of like who had diabetes was relevant to determining offspring's birth weight was really fascinating to me. And people have certain theories to kind of expand upon that. And I'll kind of go into that a little bit. So one thing to look at the relationship between maternal diabetes and higher birth weight is relating to the overnutrition hypothesis. So it's kind of related to that original Barker hypothesis, in that there's a vicious cycle of risk of diabetes that can be propagated intergenerationally. And a lot of us are probably aware of this just in terms of pop science, like intergenerational transmission of risk for diseases is often talked about with regard to psychology and also for metabolic disease. But here's how the cycle actually is proposed to work. And this is again from folks in my group. So first we see maternal obesity or diabetes conferring fetal overnutrition because the fetus is exposed to an excess of nutrition in the uterus. And then later on, the fetus is more likely to develop into a child or adolescent that has early onset diabetes or obesity that can later cause diabetes at an early age. And then if as an adult they have diabetes, then they're more likely to potentially expose their children, their fetuses, to in utero diabetes or hyperglycemia, basically like an excessive amount of sugar in utero, which can confer higher birth weight. So this cycle can kind of be perpetuated over generations, is what this hypothesis kind of supports within this larger Barker hypothesis. So there's also the fetal insulin hypothesis. So this is something which in short proposes that if in utero you have hyperglycemia, basically an excess of blood sugar, because basically pregnancy is a state of inflammation with reduced control of blood sugar. That's something that we might be aware of, like oftentimes in pregnancy, a healthcare provider might tell us, just watch your blood sugar. You don't want to be at risk of gestational diabetes. So that's something that relates to this left-hand panel. And then hyperglycemia in utero can confer risk of fetal hyperinsulinemia. Basically, the fetus, as it's developing, can then secrete a bunch of extra insulin in response to that environment, because the fetus is basically swimming in a soup of extra sugar, which I didn't know before, actually. So the fetus is actually potentially secreting a bunch of extra insulin. And because insulin is a growth factor, a trophic factor, then that can cause the fetus itself to grow excessively and then lead to a greater offspring birth weight. So that's this mechanism, the fetal insulin hypothesis. So basically, overall, there's this shared genetic predisposition to hyperglycemia. So if the mom might have a genetic predisposition to hyperglycemia, maybe a disposition to type 2 diabetes, then that can confer a greater birth weight in the offspring or a lower birth weight in the offspring and a higher risk of diabetes later on, kind of indirectly. So kind of complicated, but all these different hypotheses kind of go together and try to play into what this kind of U-shaped relationship between type 2 diabetes and birth weight could really mean. So what did I do my research in? My research is mostly taking place within a cohort, and this is a longitudinal study of health that's involving members of an indigenous community that is from the Southwestern United States. And just a note, a lot of research has gone into like indigenous genomes in research. And one thing that's been expressed by this indigenous community is that they prefer not to be directly named in research studies. And great research has been done and papers have been written by Keolu Fox and Crystal Tosi on this matter. So really highly recommend this. This community has a relatively high prevalence of type 2 diabetes. And there's over 10,000 individuals in this study that were examined over time, many of whose family members were participating in the study. And over 7,700 people had genotypic data available in the study. So multiple generations of families, also siblings, allow for the study of disease risk that's propagated over generations and kind of testing what these hypotheses mean within this population. So I kind of did a refresher to just analyze the relationship between birth weight and type 2 diabetes within this cohort to see if the relationship was U-shaped. So I did a quick analysis, splitting the individuals into categories of birth weight. So each category didn't have the same number of individuals, but they were preset in terms of the range of grams. So on the lower side, categories 1 through 2, and then on the higher side, 5 through 6. So going here, we see that basically in splitting individuals into these categories, we can see a U-shaped relationship that is significant. And then the prevalence of type 2 diabetes is on the left-hand column. So this is, like Omar said, just a summary of a couple sub-projects within my PhD research. And I just wanted to summarize this directly under this birth weight diabetes umbrella. And number one is, this question was, what are the genetic associations with birth weight in the NIDDK cohort? And then question 2 was, how does a polygenic score for type 2 diabetes contribute to the prediction of the incidence of type 2 diabetes? Basically, over time, a person developing diabetes over a given number of years versus commonly measured clinical variables. So I'll get into why asking those questions one by one. So first, what are the genetic associations with birth weight in the NIDDK cohort? So first, there's a type of research methodology called a genome-wide association study. And I'll just summarize some of the really important work that's done by a group led by Warrington et al. A couple years back. So a genome-wide association study is a pretty fascinating type of study that emerged over the past few decades. And it lets you identify the most significantly associated points in the genome, basically that can vary. So genetic variants or single nucleotide polymorphisms, basically at a single letter in the genome, what points in the genome are associated with a certain trait, like type 2 diabetes or like birth weight. So both of these traits have many different efforts to identify different important genetic variants that are associated with them. So for one of these recent efforts, it was quite huge. Hundreds of thousands of people were included in this meta-analysis. There were a bunch of different studies in individuals that were conducted over time. And then Warrington et al. Brilliantly combined all those different individual studies to kind of pool them and then identify what were the most important genetic variants that were associated with birth weight across all those hundreds of thousands of people. So they identified over 200 genetic variants or SNPs that are significantly associated with birth weight at a genome-wide level. And that's, if you've heard of p-values, that's oftentimes what we use in genetics. And it's a flawed mechanism if you just use it itself, but this is the number of SNPs that were significantly associated with birth weight in that meta-analysis. And also what they did, which was really brilliant, was they did separate maternal and fetal GWAS. So they analyzed data, genetic data from moms as well as from offspring of them to look at the genetic variants that were associated with the offspring's birth weight. So for the maternal GWAS, that was looking at the mom's genotypic information that was associated with how much the offspring weighed when they were born. And for the fetal GWAS, that was looking at the offspring's genetic information that was associated with their own birth weight. So pretty complex analysis, and it takes quite a lot of like computation as well as kind of matching mothers and offspring to be able to even conduct that. So I can't even emphasize how huge of an effort that was across all the different studies. So what they found, I'm not going to go into each individual genetic variant, but what was pretty brilliant was they identified not only variants that were significantly associated with birth weight within an offspring themselves, but because they conducted two different genome-wide association studies, one for maternal genetic information and one for fetal genetic information, they found 5 different categories of variants. So some not only were fetal effects, so basically within the fetal GWAS, it was basically they were only significantly associated with diabetes within that GWAS. There were also, number 2, variants that were only identified as significant in the maternal GWAS. There were some variants that were shared between the GWAS. So stuff that basically acted in the same direction with respect to birth weight between the maternal and fetal GWAS, and some that worked in opposite directions. So it kind of canceled out if you were to analyze all the people pooled together. So it just shows that even between mother and offspring, parent and offspring, a fetus, an offspring can inherit genetic risk for birth weight and diabetes, low birth weight or high birth weight and diabetes. But the kind of direction of the relationship between those variants can differ based on whether or not they inherited it from their parent or not. So this is just a really complex kind of intersection of genetics and early growth, and I thought that was important to highlight. Going on. So what I did to follow up, I conducted 7 different genome-wide association studies, or GWAS, but this is just summarizing one of them to kind of follow up on this previous research. So this was on a substantially smaller data set of 3,700 people, when the previous GWAS meta-analysis included hundreds of thousands of people. So what that means is there's substantially less power to detect associations, and that's what we ultimately ended up finding. But it was just important to us to look at this within this population because we were doing other analyses of birth weight and diabetes in this one. So 3,700 people were included in this study, and their own birth weight was recorded from medical records or birth certificates, and a genome-wide association study was conducted. And again, so the trait of interest was birth weight in grams, and then genotypes were looked at across the genome, 5 million variants. And then what that consisted of, across the whole genome, single variant association tests were done to look at whether or not certain letters that could vary at various points in the genome were associated variant by variant with birth weight, that trait of interest. And what you get as the output of GWAS, maybe you've seen this, maybe you haven't, but this is called a Manhattan plot because it's supposed to look like the skyline of New York City. So you see on the x-axis, you see the chromosome goes from 1 to 23, meaning all the numbered chromosomes plus the X chromosome. And also the inverse logged p-value, which is basically an indicator of how significant the association is. So the higher the degree of significance, then the higher it'll be physically on that graph. So you see chromosome on the x-axis and then the significance on the y-axis, basically. So here's the findings of my GWAS, and it's hard to kind of quantify, what is the importance of this. But the main thing I wanted to say is that we see one standout variant that's of relatively high significance, but it doesn't match this standard definition of what genome-wide significance is. And this is a variant, like the highest one here in SIR1 ABCC8 was identified previously as associated with birth weight, as well as associated with diabetes in this same cohort. So why is that important? So while it wasn't shown to be genome-wide significant, which is usually kind of warranted, it kind of prompts future studies regarding this variant. I just thought it would be important to note because it has some similarities to other variants that are known to cause a condition called fetal hyperinsulinemia, and also this other one called neonatal hyperinsulinemic hypoglycemia of infancy. So that's a condition that can cause one to have increased birth weight and also predispose somebody to have early onset diabetes. So this variant has been shown from others in our group in a brilliant paper before to be related importantly to diabetes and birth weight. And so this finding, while it's not significant on a genome-wide level, it does support the fetal insulin hypothesis if this is a true association. But yeah, more people would be needed in the GWAS to be able to have enough power to really detect whether it's a real association. But it's definitely suggesting that, this variant could be important within this cohort study. All right, so the second and last project that I want to summarize is type 2 diabetes polygenic scores, or PS, and type 2 diabetes incidence. So this project looks at something that's a bit unrelated, which is a polygenic score that kind of summarizes the findings of genome-wide association studies for type 2 diabetes and looking at the incidence of type 2 diabetes later on. But why does that relate to birth weight? I'll explain that in a moment. But basically, why we would do this type of analysis, it's to kind of compare the contribution of clinical variables that you could get measured in a clinic in a doctor's office to genetic information that's distilled down into a polygenic score to predict the incidence of type 2 diabetes later on in life. So what could that be used for? Well, in clinical settings or in, say, looking at research studies, you could stratify patients on how at risk they are for diabetes if you already have genetic information to calculate a polygenic score. And then you can also look at maybe prognosis or kind of forecasting whether or not a person might get diabetes in a certain number of years, and also prevention. But that kind of depends on what genetic information you already have available, which is pretty limited overall right now. So what is a polygenic score? So remember that Manhattan plot on the left-hand side that I had? So this is exactly that one, just taken as an example, but kind of impose that on this image. So this is just turned to the side just so it's easier to see. But polygenic scores are mainly coming in two forms. So this is a diagram from one of my supervisors, and they constructed it so that there's two different kind of constructions of polygenic scores. So on the left-hand side, the RSPS is basically if you take this line, this gray line that's right kind of to the right on that Manhattan plot that's been turned to the side, and then only shave off the points on that Manhattan plot that are higher than that. So you kind of restrict to a certain threshold of significance the variance that you want to include in that polygenic score, and then use the variance in a genotype. So what letters a person has at that point in the genome for each one. And then calculate a polygenic score for an individual only for those significant SNPs. Then you have basically a polygenic score for each individual that you can use in certain research studies, or maybe for trying to look at a person's risk of diabetes. And then also kind of extending that, there's a global extended polygenic score. So again, the same concept, but you can take, say, for a much lower threshold or for all variants across the genome, so all those dots on the Manhattan plot, and calculate using data that's already available from a genome-wide association study, a score that kind of distills down all the information from all those variants in the genome for a given individual, and then calculate basically a number that distills down what a person's genetic risk or genetic predisposition for a complex trait like type 2 diabetes might be. So yeah, this is a really important hot topic in genetic epidemiology research, because for complex traits that are influenced by so many different variants, this doesn't tell you, what your risk definitely of developing this disease is, but maybe across a whole population, you can kind of see a distribution between polygenic scores and then risk of later disease. All right, going on. So for a review of previous literature, most previous studies on polygenic scores for type 2 diabetes and type 2 incidence have been in adults. The current study, what I'm going to summarize for you, focuses on a subset, basically a birth cohort within this NIDDK cohort. But what's available and what I've done in my overall PhD research is look at findings for 3 different cohorts with different age ranges at baseline, basically at their first exam that's available. So there's a birth cohort, a youth cohort, and adult cohort. So what do those look like? So on the top, there's the adult cohort, which is about 2,300 people. And the baseline exam was at least 20 years of age. And this is the number of cases of diabetes, so people who had diabetes, and the number of person years. So for the number of people that were included, the amount of time that all people had participated in the study from this sub-cohort. So there's also the youth cohort just below that. And that has a baseline exam at age 5 to 19 years. And then for the birth cohort, this was kind of a simulation because we didn't truly enroll, we didn't truly have people who had enrolled at birth in this study. People could enroll from age 5 and up and then be followed up over time. But this was a cohort that was constructed using data that would be kind of available at their birth. So to look at the different clinical predictors for people in each of these different cohorts. For the adult cohort, you have the demographic variables, age and sex, and also clinical variables. So parental history, basically whether or not a parent had diabetes. BMI, which is an imperfect measure of adiposity, but it was what we had available, just important to acknowledge. HbA1c, which is a measure of glycemia over time, and also fasting plasma glucose. And kind of similarly, similar demographic variables, but a slight difference for clinical variables. There was a slight difference in how we calculated the measure for BMI. We calculated BMI Z-scores to capture people who had relatively high or relatively low weight in the youth cohort. And that's just something that some colleagues have demonstrated over time is important to do in analyses of youth regarding diabetes, metabolic health, obesity. And also a birth cohort, which I mentioned, kind of only had a couple variables that were available as if we had collected them at birth. And why do that? To kind of look at using the information that a person would have, say at a doctor's appointment, then how much information would genetics on top of these clinical variables add? So the same demographic variables, except birth year was used instead of sex because age at birth would be 0. And also clinical variables, birth weight, which we partition into high birth weight versus low birth weight. And also parental history of diabetes would be available at birth. So that's what we chose to include. So type 2 diabetes polygenic scores were used. So I had to construct them. So using a previous genome-wide association study, I took the genome-wide significant variants that were identified in a really big, really huge study over hundreds of thousands of people, again, by one of my supervisors. So that was over 400 genetic variants. And then using genotypes, basically genetic data from the NIDDK cohort of just over 7,700 people across 5 million different variants. The overlap between that was about 3/4 of the original 403 variants. So the overlap was 293 variants. And we think a lot of that was due to certain variants being super rare in this cohort, which can happen. And also, so how did we calculate them? So in genome-wide association studies, you not only get a measure of the significance of the association between variants across a genome with a given trait, in this case, type 2 diabetes, but what was found in the diagram meta-analysis, that one by my supervisor, there's an output called a beta coefficient, and that's basically a measure of the strength of association rather than the significance of it. So that strength of association, that beta for a given genetic variant, was multiplied by the number of risk alleles, basically the number of letters that a person had at that point in the genome, that letter being the letter that puts a person at risk for having type 2 diabetes, which means risk alleles. And so across those 293 variants in that overlap between that previously existing study and then the variants, the genotypes that were available in this cohort, then this product between that beta coefficient and then the number of risk alleles for a given individual was summed up. And then for a given individual, then they have that sum of the products, which is a polygenic score. So that's how that's calculated. And so just to show briefly, over 30 years, basically over 30 years of follow-up or until a person dropped off from the study due to loss to follow-up, or maybe they developed type 2 diabetes, the cumulative incidence of type 2 diabetes by the category of polygenic score, so the octile of polygenic score on the x-axis was shown here. So basically just not adjusted for anything else, as you increase in the, basically in the number of the polygenic score. So 8 being very high relatively and 1 being very low, then you see that type 2 diabetes has a higher cumulative incidence. These things are positively correlated, increases up as we go right. And also a way to measure how good a predictor is, basically predictive accuracy, is called the area under the ROC curve. So the ROC curve is a plot of the true positive rate. So when things are identified as cases, and that's correct, as a function of the false positive rate. So identified incorrectly as cases. And the area under that curve is a measure of how well that a given model can distinguish between cases or non-cases. So if a person developed type 2 diabetes or did not. So a weakness of this is that you have to input a whole model, basically including a bunch of different predictors in addition to a model, in addition to a predictor of interest. And it doesn't assess the individual contributions of each of the predictors in the model. So going from the left-hand to the right-hand side on the horizontal axis, if you just have sex, the left-hand panel, so the light blue is without the polygenic score. So sex alone wasn't that great of a predictor of whether or not a person would develop diabetes in this population. But then when you add the polygenic score, there's a quite big increase. So the light blue versus the dark blue. And individual kind of statistics, if you're interested, are listed just above with the polygenic score column. And then as you add more clinical variables, so as you go to the middle and add parental history, then that baseline model actually performs a bit better than sex alone. But then when you add the polygenic score, there's still a substantial improvement. But then when you add birth weight, to that model of sex and parental history, that base model performs a little bit better yet. And then you still have a substantial improvement when you add the polygenic score on top of that. So this is kind of connecting this theme of looking at the relationship between birth weight and type 2 diabetes. So to give you a sense of how polygenic scores have tended to perform with regard to predicting diabetes, I'll summarize that in a minute. So this is a review of previous literature. We don't need to go through everything, but basically previous studies have included kind of increasing numbers of variants in polygenic scores and then kind of compared how they perform when they're added to a bunch of other clinical variables in predicting type 2 diabetes. And looking at the left-hand panel here, the Meigs 2008 study, we see that a baseline model without the polygenic score performs relatively well. Like an AUC, an area under the curve, can be up to 1.0 usually, and this is 0.9. And then the AUC of the model with the polygenic score included is just 0.001 better. So that's not substantially better. And then we see a similar theme, like the AUCs tend to be reasonable, and then there's a very small incremental improvement when you add the polygenic score to the model of clinical factors. So that theme continues, and that's what I've seen as I've looked at other literature. And then going on here, I've plotted basically a summary, a scaled value of the polygenic score, and then kind of differentiated based on kind of this summary of clinical variables in percentile groups. So 5th up to 95th in this little legend here, and then plotted that against the predictive cumulative incidence of type 2 diabetes. And basically what I want you to see is that overall you see a consistent increase in each of those curves by color as we go from low to high with respect to the scaled value of the polygenic score. And you see that if you have a clinical linear predictor that's really high in terms of percentile, so basically your clinical risk is really high already, then that tends to really like differentiate this one dark blue curve in the y-axis, the percentage of cumulative incidence of type 2 diabetes. All right, and then lastly, this is an analysis that kind of addresses the weakness of that previous area under the curve analysis. So the net reclassification improvement kind of gets us to ask, so what percentage of individuals are correctly reclassified in their proper group if you include a given variable into a model in addition to the other ones in this group. So basically, when we add the bottom row, the type 2 diabetes polygenic score, to a model that has sex, parental history of diabetes, and birth weight, then 30% of people are reclassified correctly. And that looks similar on the right-hand side in terms of NRI to the second row, the parental history of diabetes. So that's kind of intuitive in a way. So parental history of diabetes, meaning in terms of like if you're asked at a doctor's office whether or not a parent had diabetes or a relative had it, that's the information one would have. So that can kind of relate to the genetic variants that you might inherit from your parents that are important for determining type 2 diabetes risk. So I thought that was an interesting finding. But just to summarize everything, so project 1 was about identifying genetic variants that were associated with birth weight, and no variants reached genome-wide significance. That was probably due a lot to small sample size. And also this highlights the this variant, the SIR1 ABCC8 variant, as a potential variant of interest that might merit future study. But it's hard to conclude anything just because there's no genome-wide significant variants from this relatively small study. And then project 2 was about looking at the incidence of type 2 diabetes, trying to predict that using clinical variables and or a polygenic score for diabetes. And focusing on the birth cohort, so like birth weight and some variables that you'd have at birth. So the added information of the polygenic score to the overall prediction model was pretty modest, and the clinical variables predicted type 2 diabetes and incidence like decently overall when you included all of them. And there was a similar net reclassification improvement, that last analysis, for the type 2 diabetes polygenic score and parental diabetes. So further work's needed. There's not many studies that look at what information you might have at birth or at youth, and then looking at the long-term risk of the long-term prediction of a person's development of type 2 diabetes. So that might be useful to do more work on, given that a lot of people tend to look at kind of just life course epidemiology or genetic epidemiology and not try to kind of compare how much information comes from genetic variants versus how much information might come from clinical variables in predicting diabetes incidence. Like what's the interplay, and also how much does genetics add to clinical information? All right, and that's the conclusion. Thank you, everybody. And then if you have any questions about, kind of pursuing a PhD, or if you want to participate more in Diabetes Journal Club, feel free to, and feel free to email me. I'm happy to leave my email at the end of the session. Cool, thanks.
Thank you, Lauren, for a great overview on your PhD project. And then I will stop the recording now and we will pass on to the Q&A. Thanks for that.